Hello, everyone. I trust you are all well, and welcome to another session of the Innovation Week. My name is Rui Queiroz, and I am a part of the applications team here at Hyperbaric. In this session, my colleague Dr. Mario and I will talk a bit about advances in high-pressure thermal processing. I will start, and then I'll give the word to Dr. Mario. So what is high-pressure thermal processing and how does it work? In simple terms, it's just HPP at moderate or high temperature. By moderate temperature, I mean below 90 degrees Celsius, and above that, we consider it to be high temperature. It is noteworthy to mention that at some processing conditions, you can even achieve sterility. The flow diagram is very similar to standard HPP with a couple of extra steps that you can see on the screen. First, the first extra step is that you have to preheat the products and the carriers. Then it's just like HPP. You load the carriers into the vessel, fill the vessel with low pressure water, pressurize it, hold the pressure, decompress, unload the carriers from the vessel, and then it comes to another extra step. That is to cool the products down. How does it work? Well, when you compress something, you generate heat, and the more you compress it, the more heat is generated. On the graphic on the left, you can see an example on how the temperature increases with pressure. Of course, the rate and total increase depends on the properties of the food and materials. Different foods and different materials heat up differently. And when you decompress, you release all that accumulated heat and the products cool down immediately. This temperature increase and decrease are almost instantaneous and occurs in all the products simultaneously. So there is no differences between the inside and the outside of the product. The advantage of this is that you get synergies between the pressure and temperature. And most of all, you minimize the time that the product is exposed to temperature, which is not very good to be at high temperatures for a long time. On the graphic on the right, you can see an example of the comparison of high pressure thermal processing with the conventional heat. In the HPTP, you preheat the product to a predetermined temperature, and then you do a pressure cycle. As you can see, the exposure to heat is much shorter when you combine pressure and temperature. You can see more details on how it works on the session from the 2021 edition of the Innovation Week, given by Dr. Snozer and Sevenich. In this session, we will focus more on the applications of the technology and the equipment and engineering aspects. So let's start by browsing some of the applications that are already authorized to use this process. Our first example is the patent process for processing milk by Naturo, an Australian company. I took this flow diagram for their patent that explains the process. First, there's an homogenization step below that has a maximum temperature of 60 degrees. Then it goes to the filling line. Then you have to preheat the product to be somewhere between 33 and 37 degrees Celsius. Then you do a pressure cycle, about 600 megapascal for 3 or 4 minutes, never surpassing 60 degrees. And then you have a cooling step. This high pressure thermal processing of milk gives it 60 days shelf life at refrigerated conditions, ensures safety and minimize flavor changes, and is accredited by the Safe Food Queensland, Australia. As far as I know, it's not commercially available yet. Our next example also uses moderate temperature. Here we can see the authorization letter for high pressure thermal processing of foie de gras. I believe I murdered the accent. From the French Scientific Assessment Agency for Food and Nutrition. The processing conditions are somewhat similar to the previous example. 600 megapascal for 10 minutes at 60 degrees, and we can achieve a shelf life of 90 days at refrigerated conditions. Our next example combines pressure with high temperature, higher temperature here, 121 degrees Celsius, and was approved by the FDA for the production of sterile and shelf-stable mashed potatoes, low-acid food. Next is a similar application to the one before. Here we can see the authorization letter from the FDA for the use of HPTP for commercial production of shelf-stable, low-acid, ready-to-eat meal, which I believe, if I'm not mistaken, that is pork with garnishes. So now let's talk about the available equipment for high-pressure thermal processing and the main challenges for its implementation at the commercial level. To validate industrial processes, we first need to identify the critical parameters of the process. For HPP, we just have pressure and holding time that can be easily monitored and recorded. But when we add temperature, we get another critical parameter. Contrary to pressure and time, temperature presents some challenges in its direct measure, as we will discuss in the next minutes. In this case, alternatively, we can validate temperature via indirect measurements. So if you know the vessel temperature, the temperature of the pressurization fluid, and the product initial temperature, you will know the temperature inside the vessel and the product. As we just seen, the critical parameters necessary to validate high-pressure thermal processing are pressure, time, and temperature. That is to say, we need to guarantee that the product is subjected to a determined pressure for a determined time at a certain temperature, no matter its position on the vessel. Pressure is uniform throughout the vessel and product, so there's not a problem there. Holding time is a fixed parameter, so 5 minutes is 5 minutes. That's no way around it. However, there is the development of temperature gradients in high-pressure thermal processes, and this is a problem. The causes for these temperature gradients are the lack of heat of compression of the vessel and the plugs. Steel doesn't heat up due to compression heating, so it stays at the initial temperature, and it causes a difference of temperature between the product inside and the products in the middle of the vessel and the product near the wall of the vessel. The vessel design also creates different temperature gradients because of the position, if it's horizontal or vertical, and the different properties of the materials involved lead to differences in temperature as well as heterogeneous food products, different product packaging material, the material of product carriers, and the temperature of the pressurizing fluid and the pressurizing fluid itself. There are some strategies to improve the temperature uniformity, namely the carrier material selection. We can choose a material that has a similar compression heating to the product that we are processing. Control the vessel and the vessel wall and plugs temperature to don't get that difference that I was talking about. Control the pressurizing fluid temperature. The compression rate and vessel filling rate also influences. And we can use alternative systems, as my colleague Mario will talk about a little bit later. So it is not surprising that some strategies are needed to monitor the temperature inside the different spots of the vessel. Some of these strategies are direct measurement. The use of sensors or temperature probes. that direct measure the temperature. This allows a continuous monitoring, reading, and recording. The problem is that some are likely to fail after a small number of cycles, and the apparatus that you use to measure the temperature may affect the temperature gradient by being there. Then you can use pressure, temperature, time indicators. These are biological active proteins in buffer solutions. So if you know that an enzyme, let's say, it's inactivated at a certain condition, that's a certain combination of pressure, time, and temperature, and afterwards you analyze that enzyme activity and you see that it's zero, it means that you reached the combination that you intended. These are robust, cheap, small, and widely employable sensors. However, different combinations of these three parameters may have the same result, which may be an issue. Another way is by using computational fluid dynamics. These are numerical simulations and mathematical modeling that provide reliable, time-sensitive, and accurate temperature mapping. However, you need to validate before you have to confirm the readings using direct measurements that I mentioned before. Wired thermocouples fitted through the plugs are the most common approach in laboratory machines, where one of the plugs is usually fixed, it doesn't move. However, in industrial machines, both plugs move, making it very easy to damage the thermocouple. Moreover, this solution only allows for temperature measurements near the plugs. We don't know the middle of the vessel, the temperature. At Hyperbaric, we use two types of temperature sensors for tests with temperature that we place inside the carriers. On the left, you can see a wireless high-pressure temperature sensor developed by Hyperbaric. It can withstand 600 megapascal, a little bit more, and you can read temperatures up to 130 degrees Celsius. It transmits data wirelessly after each cycle, so you don't have to connect it to anything. But it has a large metal body that can act as an heat sink. As I said before, metal doesn't heat up with compression. So it may create some gradients. As you can see, it's quite large by the measurements on the figure. Another sensor that we use is one developed by CSIRO. We call it ThermoEgg. It withstands a maximum pressure of 800 megapascal. Maximum temperature under pressure is 125 degrees Celsius. But since the sensor is inside a shell, there is a slow heat transfer. The heat has to travel between the outside of the shell into the inside, to where the temperature sensor is. So this requires some data correction. I would like to highlight that most studies that you can find in the literature are conducted in laboratory machines. So it's difficult to translate it to what would happen in bigger machines. There are only a couple of pilot scale units in the world. Hyperbaric has one of those installed in ASTI, an research institute in Spain, and it's an equipment available only for research purposes. It has thermal regulation of the pressure vessel and plugs, heated pressurization fluid, wired thermocouples on each plug. So we already addressed some of the issues that I mentioned before. It can go up to 630 megapascal and a maximum temperature of 130 degrees Celsius. It is the size of our smallest machine, that is 55 liters. So the main challenges for industrialization, it's it's a summary from what I've been talking about. Maintaining and measuring the temperature that requires thermal regulation of the vessel and vessel wall and plugs. The creation of temperature gradients that depends, as we've seen, on several variables. Scale up is also difficult due to high costs, reliability, technical challenging. Productivity is also affected because you need to preheat the vessel, and that can take a long time. It requires automatic handling as processing at temperatures above 50 degrees may present safety concerns, for example, burns. And then you have to do biological validations, which are difficult because the lack of pathogen surrogates, and chemical validations to make sure that you don't form unwanted compounds or induce packaging migration. New alternative systems have been developed that address most of the previously limitations, namely specialized carriers for high-pressure thermal processing that allow using standard HPP machines. Dr. Mario will give more details on this right away. Don't forget to visit our website to access a world of information of HPP. And with this, I finish my part of the session. I hope you found it useful. And now let's hear Dr. Mario giving us more information about those specialized carriers that I've mentioned. Thank you.
Hi, everyone. So we are in our workshop, and this is a very nice place to present one of the latest innovations for high-pressure thermal processing. I am standing right next to a hyperbaric 420-liter machine. And as I said, this machine is very suited to explain this new process. I have here this isolated canister, which can be used for high-pressure thermal processing applications. This canister can process food products up to 130 degrees Celsius or 265 degrees Fahrenheit. Okay, so the design of this canister is very simple. But there is a lot of science behind for the development of this canister. It is composed of 3 different plastic layers that give a perfect isolation to the system. We have here the inner layer, which is composed of high-density polyethylene. We have an intermediate layer, which is composed of polypropylene. And finally, the outer layer is composed of Teflon. So these 3 layers create perfect isolation for the products that we place inside. Finally, the canister is closed, as you can see here, by a piston that goes here. So this piston is also a key thing of this innovation because it moves inside the canister as we build pressure. So this is one of the reasons that, why this canister can withstand up to 6,000 bar or 87,000 psi. The big advantage of this canister is that it can be used in commercial machines, as you can see here. So even if the machine operates with cold water, the design of the canister still creates the isolation inside. Now I will explain how the process works with this canister. So this is the final position of the canister, but before that we need to prepare the system for the cycle to start. So firstly, we would need to preheat the different plastic layers of the canister with hot water with the target temperature that we want before the cycle starts. On a different tank, or it can be the same water tank, we also need to heat the products that we are placing inside. So once we have everything at the same target temperature, the canister is filled with hot water and hot product, and the piston closes the canister. You see here 2 plastic bolts that must be screwed to to close the canister and to create the isolation. So once this is ready, this can be done by robots just to make the process more automatic. And you also have to consider that we are working with hot water, so robots are very convenient for these operations. And once this is ready, the canister is placed in the conveyor of the machine and is pushed inside a commercial machine. And as I said, even cold water can be used to pressurize the whole system. So now I would like to go through some slides to summarize this process. I haven't mentioned that, but the design of this canister is patented. CSIRO, the Australian Research Centre, developed this innovation, and with Hyperbaric we have an agreement for the commercialization of this type of canisters. As I said, the system is isolated and composed of different plastic layers, and yeah, the piston moves inside the canister as we create pressure. So this is perfect for food applications. Here you can see a smaller version of the canister that we use to validate the process and for trials, and the way it was preheated. We inserted hot water and we were like recirculating hot water inside the canister just to reach a target temperature. You can see also a graph with a temperature profile, and you can see how stable the temperature was under pressure. So in this example we reached more than 120 degrees Celsius, and you can see that temperature was maintained for 3 minutes at 6,000 bars. As I explained, this is the process. We need to preheat the product on one side, and we also need to preheat the canister on another side. Once the system and the product is preheated, the canister is filled and pushed inside a standard HPP machine. And the whole system is pressurized, and then the canisters are released from the machine. And again, we have to remove the plastic bolts that we placed on the piston to close it. So we have to remove them, just to remove the piston, empty the contents of the canister, and cool down the product. Okay. So this canister is ideal for high temperature applications. This is a generic range, but you can see from 60 Celsius or 140 Fahrenheit up to 250 Fahrenheit or 121 Celsius, but it can withstand even higher temperatures, up to 130 Celsius or 265 Fahrenheit. So since this works with very high temperatures, one of the advantages is that we can inactivate bacterial spores to create chilled stable or even shelf stable products depending on the temperature we target. We have a reduced quality loss and nutritional loss because the time that the products are under high temperatures is reduced. And there is also a potential reduction of food processing contaminants associated to intense thermal treatments. Here I show you some literature that supports this idea. This particular study was conducted on milk, and the target microorganism was proteolytic Clostridium botulinum spores. So on the one of the graphs, you can see the inactivation of Clostridium botulinum spores with standard thermal processing, and on the right side you can see the inactivation of the spores with a high pressure thermal processing. And you can see that the time required to achieve similar log reductions was reduced more than 10 times when using the high pressure thermal processing technology. Of course, you can also see that the higher the temperature under pressure, the higher the inactivation. And you can see that less than 5 minutes under 6,000 bar, 7,000 bars, sorry, of pressure in this particular study already achieved close to a 5 log reduction of spores. This second study was conducted on different food products, very wide range of ready meals, and it assessed the inactivation of proteolytic and non-proteolytic spores. You can see on the left that proteolytic spores can be controlled with this combination of high pressure and temperature, achieving more than a 5 log reduction with less than 5 minutes of the duration of the treatment. And non-proteolytic spores can be also controlled, but since they are more sensitive to temperature, we could reduce, the study reduced the temperature for the inactivation of spores. And you can see that, it is possible to achieve a significant log reduction of bacterial spores, even in complex food matrices. Now I would also like to present a similar innovation, but for a moderate temperature applications. This is a different type of canister that was developed by us, by Hyperbaric. We also have a patent application for the design of this canister. And it is similar, but with some differences, okay? So this canister is not isolated as the one I presented before, but it has some tiny holes on top, just to minimize the exchange of water, the water inside and the water creating pressure outside. And it has a bottom plate that creates isolation. You can see the diagram here, and here you can see some pictures of the real canister, okay? You can see on the left that it has only a few holes on top. You can see also the plate that I mentioned on the bottom that creates isolation. And you can see also how the canister was filled, in this case with plastic bottles of milk. Here you can see how we validated the canister. We used a thermocouple and a temperature probe that is able to withstand high pressure. So you can see here how we were placing the thermocouple in one of the milk bottles inside of the canister. And you can see also the canister was already in one of the conveyors of the machine. And again, you have a pressure temperature profile, and you can see that the temperature remained stable during holding time, okay? So this was a cycle at 6,000 bar for 3 minutes. And the good thing is that you can see how the temperature was stable during the holding time. So the mode of operation is quite similar. In this case, everything is preheated at the same time. The canister is filled with product, and the filled canister is placed in a water bath just to reach the target temperature. Then the canister is placed in the conveyor of a standard machine and pushed inside the HPP vessel. For this particular application, the water that creates the pressure needs to be preheated as well, okay? So we have to preheat the pressurization water and the water surrounding the canister just to minimize heat exchange. And once the cycle is completed, we just have to empty the contents of the canister and cool down the product. This process has some advantages. We have an increased shelf life compared to a standard HPP at chilled or room temperature. We have an enhanced pathogen inactivation on specific applications, for instance, dairy products. We also have an enhanced enzymatic inactivation to create more stable products under refrigeration. And apparently the digestibility of some nutrients is also increased on certain applications, but this has to be assessed case by case. So with this presentation, I hope you have a clear idea on the different solutions that we have nowadays for high pressure thermal processing applications. And if you have any questions or you want to explore this process, we are open to run trials. We have a pilot plant and we can operate this type of canisters on your products. So you just have to contact us. Thank you for watching.